This is a continuation of the BocaPhysics Introduction to Particle Physics. Now, in the previous lecture, we started talking about a bunch of the kinds of particles that were observed. We talked about muons, we talked about pions, we talked about antiparticles. Now, it became clear pretty immediately that these particles needed to be classified some way. So originally they were classified according to mass, and that certainly seems like a reasonable thing to do. And you have leptons, mesons, and baryons. That means lightweight, middleweight, and heavyweight. But that became clear that pretty soon that really wasn't a really good way of classifying particles either. So nowadays particles are classified according to the kinds of interactions they have. And what do I mean by interactions? Essentially, we're talking about the four fundamental forces. Although particle physicists prefer to use the term interactions rather than force. And those are, in order of decreasing strength, strong, electromagnetic, weak, and gravitational. Now, gravitational, of course, is the most familiar force of all, and electromagnetic force, or interaction, very familiar from classical physics, but we've got these two new forces, or interactions with which to contend. So how did the strong force come about? Well, if you think about a nucleus composed of protons and neutrons, with the exception of hydrogen atom, of course. And the question there is, well, we know there's such a thing as electromagnetic repulsion, like charges repel. Well, if you've got a nucleus that consists of a bunch of protons, how is it possible for that nucleus to stay intact? How is it not just, maybe explodes too hard to be the word, but how are they not driven apart? And the answer there's a strong force binding those particles together. So that was why the strong force was proposed. Now, for the weak force, it was realized that certain kinds of processes, beta decay, couldn't be explained in terms of the strong electromagnetic and gravitational. So that's the origin of that interaction being proposed. Now, both electromagnetic and gravitational interactions go as 1 over r squared. Essentially to feel their effect infinitely far away. Strong and weak forces have a very short range. Strong force has a range of on the order of 1 femtometer, and 1 femtometer is equal to 10 to the minus 15th meters. And the weak force, or weak interaction, has an even shorter range. That's 0.001 femtometer. So basically we're talking about the range over which a strong interaction dominates. It's going to dominate the electromagnetic interaction of that range. Beyond that, it drops off precipitously. So I like the way David Griffiths describes the strong interaction in his book on particle physics. He likens it as the punch of a heavyweight boxer. Okay, it's very powerful if you happen to be within arm's reach, but once you get beyond that, there's interaction drops off precipitously. So I think that's a good way of describing it. And as I mentioned, weak force, weak interaction has a much shorter range. Now, how do you quantify these? Well, a good way is from the coupling constant. So the potential energy due to the nuclear force appear to have this form, minus F squared e to the minus R naught, some constant, all over R. So the coupling constant is useful when you're comparing quantities to use dimensionless quantities oftentimes. So that's equal to F squared over H bar C. And from observations, that's roughly on the order of 1. Now, the electromagnetic, you remember what that potential energy looks like. And that's equal to 1 over 137. So clearly, strong force over the range where it is strong is substantially larger than the electromagnetic interaction. Now for the weak interaction, that's on the order of 10 to the minus 9th, and gravitational is weaker still, on the order of 10 to the minus 38. It's not believed that the gravitational interaction really plays an important role in particle physics because it is so much weaker than the rest of these interactions. We talked about last time around as well that forces are mediated. They are basically have mediator particles, which are force carriers, and the mediator for the electromagnetic interaction is the photon. And Yukawa, as I also mentioned previously, suggested that the strong force might also have might also be mediated by some kind of a particle. Now, fast forward, modern day we see things a little bit differently, and the mediator particle here is the gluon. The gluon actually mediates not between these particles that we'll be talking about, but in terms of an even smaller quantity called a quark. And for the weak particles, or weak interaction, I should say, the mediator particles are W to the plus or minus and Z naught. And those, by the way, actually have mass W particles have mass 80.4 gigaelectron volts over C squared, and Z particles have mass 91.2 gigaelectron volts over C squared. So those have been observed. Gluon has never been observed. Also, the graviton has never been observed either. So these all, the rest of these have mass 0. And those are your 4 interactions, okay? So how do I classify particles based on interaction? Well, you want to think in terms of particles that have strong interaction. And we'll call those hadrons, because the word hadron comes from the Greek word for strong. And those are further subdivided down into mesons and baryons. And then we have particles that don't have strong interactions. And we'll call those leptons. We're going to describe what characteristics leptons have and what characteristics both mesons and baryons have. So let's talk about leptons first. Okay, so now let's look at the lepton family. I've drawn a table up here on the board, and what particles belong to it? What particles don't have strong interactions? Well, the first member of this family is the electron. And I'll write it as an E with a minus sign superscript, and that's to distinguish it from its antiparticle counterpart, the positron, which I'll write as E to the plus. So each of these particles has mass 0.511 mega electron volts over c squared. I'm going to leave off the units from here on. They carry charges minus E and plus E respectively, and they're both stable. Well, so far it does seem like we're sticking with that original classification scheme of lightweight particles being called leptons, or belonging to the lepton family. The next two quantities, well, we've got neutrinos and antineutrinos. But as it turns out, we don't just have general neutrinos. Neutrinos come in flavors. So this is the electron neutrino, and this is the electron antineutrino. It's a little bit scrunched up there, so it's just a nu with a bar over it and an E subscript. Those were originally thought to have mass equal to 0, but now it's generally accepted or believed that they're greater than 0. So I won't write all that out, but just know originally they were assumed to be massless, but now I believe they have mass greater than 0. Their charges are 0, they're neutral particles, and they're also stable. Because they interact so weakly with matter. A bunch of neutrinos passing through this board right now, and it doesn't have any effect because of the weak interaction. Okay, so that's our first generation of lepton particles. Now, the muons also belong to this family, and again, I'll use a minus sign superscript to indicate this is a muon, and then its antiparticle counterpart, the anti-muon, which we'll write as mu with a plus superscript. Now, those are more massive particles, 105.7 mega electron volts over c squared, and likewise for the antiparticle as well. So clearly now, leptons don't just, the lepton family doesn't just include light particles. It includes particles that do have substantial mass. The charges, again, respectively, are minus E and plus E. They're not stable. These have a lifetime roughly on the order of 2.2 times 10 to the minus 6 seconds. So even though it's a short time compared with some of the other lifetimes of the particles we're going to discuss, that actually is quite long. So anyway, there are also muon neutrinos and muon antineutrinos. Again, mass is greater than 0, no charge, and they're stable. And that's your second generation. Your third generation consists of the tau particles. Or the tau family. Tau to the minus and tau to the plus. And those are actually very massive, having value 1,777 mega electron volts over c squared. And they carry charges minus E and plus E respectively. Again, not stable, do have a shorter lifetime. And it's roughly 2.9 times 10 to the minus 13th seconds. And you guessed it, the last two spaces, last two rows here belong to the tau neutrino and the tau antineutrino. Again, Mass is larger, or believed to be larger than 0. They don't carry any charge, and they're stable. So these are the members of the lepton family. And I mentioned, well, leptons are classified according to the kinds of interactions they have. So let's look at some kinds of decay processes that occur. Let's look at the muon. Muons were observed to decay into an electron and a neutrino and an antineutrino. So that's observed. What isn't observed is a muon decaying into an electron and a photon. So just looking at this, charge has to be conserved. That's certainly the case in both of these decay processes. However, this one has never been observed to occur, and this one does. And in fact, make this a little bit more precise because we do know that neutrinos have flavors. So this is the muon neutrino and an electron antineutrino. So to kind of organize what kinds of reactions occur and what don't, we should say what kinds of reactions occur and what reactions don't occur. There's a lepton number. And since we have seen that there are flavors of neutrinos and antineutrinos, well, there are flavors of lepton number as well. So there's the electron lepton number, there's the muon lepton number, and the tau lepton number. So basically, electrons carry electron number +1. Positron carries electron number -1. Now we've got neutrino, electron neutrino, and electron antineutrino. So those will be given or assigned lepton electron numbers of +1 and -1 respectively. Well, there are no muons up here, there are no tau particles. So all these other columns in the first generation are just going to be 0. We go through the same sort of procedure for the muon subfamily. So again, there are no electrons there, so their electron lepton numbers are going to be 0. Their tau lepton numbers are going to be 0. But I'm going to assign +1 to the muon, -1 to its anti-muon counterpart, and likewise for the muon neutrino and muon antineutrino. So you can guess how this bottom family is going to be filled in. Electron lepton numbers are all 0, as are the muon lepton numbers. Tau lepton numbers, however, are going to be +1 and -1, and +1 and -1. So now I have a new number. There's no counterpart to this in classical physics. And now I'm going to look at my reactions and see, okay, is lepton number conserved? Because number must be conserved separately. So let's look at that first decay process. And look at the electron lepton number and muon lepton number. No tau particles, so I'm not even going to bother writing that down. On the left-hand side, that's equal to 0. And on the right-hand side, we have +1, 0 for the muon neutrino, and -1 for the electron antineutrino. Okay, so far so good. Now for the muon, we have +1 on the left-hand side, 0 for the electron, +1 for the muon neutrino, and +0 for the electron antineutrino. oops, I should put a cross through there, that is equal to each other. So that's equal to each other as well. So therefore, left-hand number is conserved separately for each of these. And of course, tau, everything's 0. Every product in this has tau number 0. So in fact, left-hand number is conserved, and that's why this is observed. Now, if we look at this process, if I look at electron left-hand number and muon left-hand number, this is 0 on the left-hand side and 1 on the right-hand side. Those clearly are not equal to each other, so it's not conserved. And we have 1 for the muon and the muon left-hand numbers for the electron and the photon are both going to be 0. So again, left-hand number isn't conserved, and that's why this process is not observed. One of the other decays that we discussed previously was a pion decaying into a muon and an antineutrino. So again, charge is certainly conserved. Pions are not members of the lepton family, so all of their lepton numbers are going to be 0. The only one I really need to look at is muon lepton number, so that's 0 for the pion. On the right-hand side, we have 1 for the muon and -1 for the antineutrino. We got 1 minus 1 is equal to 0. Lepton number is conserved, so therefore this process is observed. Okay? Now, we've got another big particle to deal with, and that's the tau particle. Just by applying the rules of knowing that lepton number has to be conserved for each of these processes, well, I can write down a decay. So let's suppose our tau particle decays into a muon. That's one of the products. So what must the other particles be? Well, charge is conserved because this is carries negative charge. This one does as well. But we also have to conserve lepton number. So we've got a tau particle over on the left-hand side. So that tells me I'm going to have a tau neutrino on the right-hand side. And because I've got a muon on the right-hand side, I have to have a muon antineutrino also on the right-hand side. Okay? Lepton number is conserved here, and this reaction is in fact observed. Well, tau is decaying into muons, but they can also decay into electrons. So we have a tau going into an electron again, and just fill this in. We're going to have a tau neutrino and an electron antineutrino. This is observed as well. So these rules, conservation law was written down by knowing and looking at what kinds of processes take place and what kinds of processes don't take place. Okay? So the important thing is lepton number must be conserved, and I should say each lepton number must be conserved separately. Now the way you want to look at a muon and a tau, again, basically oversized electrons. However, leptons are believed to be fundamental particles. What that means is that they don't have any structure. Okay, it's can't be broken down any further. Now, when we look at hadrons next, we'll see that they are not fundamental particles, and in fact, a model that is widely accepted that explains the behavior of hadrons is the quark model. Okay, so we'll talk about hadrons next. This is the hadron family, and notice I filled in everything because the details get a little bit too arcane, Byzantine. So anyway, we've broken the hadron family down into mesons and baryons. What's the difference between those two? Well, first of all, we'll just talk about the mesons from some of these particles are already familiar from the previous lecture, the pion. The kaons, however, are new, probably a record to most people, and also the eta particle as well. So notice the masses, again, we don't classify particles according to mass anymore, but these are certainly more massive than the electron, but not the tau particle, which is part of the lepton family. Anyway, mesons can carry charge, some of them are neutral or have no net charge, and others have carry charge minus E or plus E. Go over one more column, let's look at spin. These particles that I've listed on the board have spin 0. So that means they are bosons. Now, down here, the baryons, notice that family are the proton and neutron, the nucleons. And then we have just a few hyperons written down as well. They too can carry charge. Proton, of course, is positively charged, carries charge plus E. Neutron is neutral, so is lambda. And we have sigma plus and sigma minus, which carry charges plus and minus E respectively, and sigma 0, which is 0. And it is possible, or not just possible, there are particles that carry greater charge than that. In fact, we'll do an example of one of those in a little bit. But anyway, the spin is equal to 1/2. So these are fermions. There are mesons, or there's the meson family that carry spin 1. And basically, the distinction between these are essentially pseudoscalar mesons, and the mesons that carry spin 1 are called vector mesons, but we don't get into any further distinction in this lecture. And with baryons as well, there are baryons that have greater spin than those listed on the board. These are just a few of the hundreds of known hadrons. If you want to get more information, you should visit the Particle Data Group's website. I do have the website listed on the BocaPhysics website, and they give details about all of these particles, the best known values, and I believe the list is updated every other year. And they also give information too about hypothetical particles, for instance, the magnetic monopole, and the upshot of that is, well, nobody's observed one yet. So, but anyway, you've got that kind of information on that site. Okay, so those are the quantities, physical quantities with which most people, I reckon, are very well familiar. The next one, though, is baryon number, and this is a new number here. You assign baryon number 1 to baryons and -1 to antibaryons, and 0 otherwise. Well, mesons are baryons, so they are assigned baryon number 0. And the baryons, all the ones listed here, are the particles. So they have baryon number 1. Their antiparticle counterparts have baryon number -1. So if you're talking about a new number here, well, you might guess, well, this is an indication you've got a new conservation law. So baryon number is conserved in every interaction. And unlike lepton number, there are no flavors of baryon number. It's just it's either 0, 1, or -1, depending on the particle. So let's talk about an interaction that we discussed in the previous lecture. We talked about how antiprotons were produced. Smash a proton into a proton, and the product of that is going to be another proton, and then yet another proton, and an antiproton. So first things first, well, is charge conserved? Absolutely. You've got charge plus 2e basically on the left-hand side, and you've got plus 2e on the right-hand side. For baryon number, got 1 plus 1 on the left-hand side, and 1 plus 1 plus 1 plus minus 1 on the right-hand side. So oops, there I did it again. I'm going to put a strike mark through there. 2 is equal to 2, so baryon number is conserved, and this process is observed. Now let's say you smash neutrons into protons, and protons into neutrons, and the product of that, let's suppose, is a proton and neutron, but then a proton and anti-proton pair. If I look at baryon number, once again, that's going to be conserved because these both have baryon number 1, so baryon number is going to be equal to 2. On the left-hand side, on the right-hand side, we've got 1 plus 1 plus 1 plus minus 1, which is 2. So far, so good. And then the only other condition or conservation law that we need to concern ourselves with right at this minute is conservation of charge. That's clearly satisfied because we just have a net charge, positive electric charge on the left-hand side, and altogether positive electric charge on the right-hand side, basically equal to plus E. So this process is observed as well. As I mentioned with lepton number, these various processes were observed. What kinds of interactions take place? And from that, you can develop conservation laws. So let's look at the neutron for a minute here. And using the conservation laws that we've already discussed, how does the neutron decay? If you look here, the proton is the only stable baryon. There are no stable mesons. The proton's stable, the neutron is not stable. It has a lifetime of about 880 seconds, so it will decay. What does it decay into? Well, first thing, we know that baryon number is conserved. So I've got 1 baryon on the left-hand side, a neutron. There has to be 1 baryon on the right-hand side. There's really only one choice here because only the proton is lighter than the neutron. So we've conserved baryon number, but we also need to conserve electric charge. Neutron carries no net charge, so therefore on the right-hand side, one of the products must also be an electron. So we'll have plus electric charge, minus electric charge, and that'll be neutron. And you might say to yourself, okay, we're good to go. We've satisfied baryon number conservation, we've satisfied charge conservation. However, remember, lepton number must be conserved as well. There are no leptons on the left-hand side. You've got a lepton on the right-hand side, the electron. And remember, each lepton number must be satisfied and must be conserved separately. So therefore, see that there's going to be a third product on the right-hand side, and that will be the electron antineutrino. So we've satisfied conservation of baryon number, conservation of charge, and conservation of lepton number. So all these processes do occur, and that's baryon number. So let's move on to strangeness. There's one last process I want to talk about here. Before we move on. This is called the delta plus plus particle, and I don't have it listed on the board. It does decay, and the question is, what does it decay into? Again, let's talk about what charge must be conserved and also baryon number being conserved as well. So it's got 2e. So what could it decay into if it's got a mass of 1232 megaelectron volts over c squared? Well, say why the decay price is proton. So that takes care of one of the positive electric charges. We need to have another particle over here that also carries positive electric charge as well. But baryon number is conserved, right? Because delta plus plus has baryon number 1, proton has baryon number 1. So whatever this must have baryon number equal to 0, and this must have charge equal to plus E. So that's an indication that we want to have a meson, and that would be the pi plus. So in this case, charge is conserved and baryon number is conserved. So that process is observed. Okay? Let's move on to strangeness. To answer that question, you need to know a little bit about how they're formed and a little bit about how they decay. So, the kaon particle, K0, decays into 2 pions. That's one of the possible processes that occurs, and it actually has been observed. Okay? So charge is conserved, but if I look over here in this column here, our K0 has been assigned strangeness 1, but yet these two have strangeness 0. Strangeness isn't conserved in this process, yet it has been observed. And by the way, the track looks something like this. You had the track be the pi plus and pi minus, and there's no track visible there for the K naught because K naught's neutral, so it's not going to be track behind. Oops, minus sign here. But you do see a V shape, so that's an indication of a decay. That if you looked at the track from a cloud chamber, or if you looked at bubble chamber tracks, okay? So that process happens. Strangeness is not conserved, but if you look at production processes, strangeness is conserved, okay? If you look on the left-hand side, the proton and the pion have strangeness 0. If I look over the right-hand side, well, K plus has strangeness of 1 and minus 1, so that's satisfied. K0 has plus 1, and sigma naught's minus 1, that's 0. And again, K naught is plus 1, and lambda naught is minus 1. So strangeness is conserved in production processes. These tend to be formed by strong interaction. And notice that the strange particles are produced in pairs. You'll never see a process like this. This doesn't occur. Strangeness is not conserved in this process. Strangeness is not conserved, it's never been observed. Strangeness is conserved here. And those are observed, okay? So this is why it's called strange. Strangeness has a strange conservation law. But basically, the production processes, they tend to be formed by the strong interaction, and strangeness is conserved in that case. And decay by a weak interaction. And strangeness, not always conserved. So how do I know about the strong and weak formation? Well, look at the lifetimes over here. If you look at the lifetime of a can, that's relatively long compared to some of the other particles. It's on the order of 10 to the minus 8th. Some of these particles down here, just listed a few of them have 10 to the minus 10, 10 to the minus 19. But as you go down, some of the lifetimes are on the order of 10 to the minus 24, 10 to the minus 23 seconds. So particles, strange particles are formed by strong interaction. They decay by the weak interaction. Strangeness is conserved in the production processes. Strangeness is not conserved in decay processes, okay? So that is a strange rule. And that is strangeness. So basically, let's summarize what kinds of conservation laws that we've talked about. We talked about conservation of energy, we talked about conservation of momentum, and conservation of charge. In addition, angular momentum is also conserved. Now, when we talked about leptons, we saw that lepton number was conserved, always. We saw that barium number was conserved, always. Strangeness, however, is not always conserved. It's conserved and strong. But not weak. There are two other quantities that we don't discuss a great deal in this class, because it would take us outside the scope of a sophomore level physics class. Isospin is conserved and strong, but not in weak or electromagnetic. I'll just abbreviate it EM. The purity is conserved and strong and electromagnetic, but not in weak interactions. Okay? So again, to reiterate, what's conserved: energy, momentum, angular momentum, and charge. Also barium number and lepton number, which I don't have written on the board. And you have strangeness, which is conserved in strong interactions, but not in weak ones. Isospin is conserved in strong interactions, but not in weak or electromagnetic interactions. And purity, strong and electromagnetic, but not in weak. Now, we really don't get into this any further. Next time around, though, we will be talking about quarks, because, as I mentioned, hadrons are composites and are composed of smaller particles, which are the quarks, and we'll discuss the quark model, and we'll talk about color and flavors of quarks, and we'll talk about those, the eightfold way, and then wrap everything up into the standard model, okay?